Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We are ready to start with the second session. This one is tools for parallel testing and debugging. And we are going to have two presentations from the University of Illinois. Darko Marinov is going to talk about the testing tools at the University of Illinois. Then Dany, who just came from the other building, is going to be talking about refactoring. Then we will have Koushik Sen, hey, who just got tenure. From UC Berkeley, talking about active testing and concurrency. And finally, Chatterjee, right here, is going to, from Microsoft, is going to be talking about fighting concurrency bugs with advanced static analysis technology. This is going to be a very compressed session. We may or may not finish by 12, because we will have lunch. So if we can make it probably 12:15, because lunch is going to be in the back wall, that's going to be okay. So. Sorry? Yes, both. True for both. Okay. So please, let's welcome Darko Marinov from Illinois, and he's going to be talking about UIUC testing tools.
Hey, thank you. Can you just close this? Yeah. Okay. So, thank you. So yeah, I'll be talking about some work we've been doing on testing for parallel code at Illinois. This is a short presentation. I'll focus it on my work, but there has been other by other colleagues as well. So we've seen in the previous session that people say it's difficult to develop multi-threaded code. I usually like to make that a bit more precise, to say it's difficult to develop correct multi-threaded code. I think it's very easy to develop the incorrect one. There's just not the one that we want. And it's very easy to introduce all kinds of these bugs, races, deadlocks, atomicity violations. Mostly come due to the non-deterministic scheduling. So not only it's difficult to develop this code, but it's also difficult to test multi-threaded code. So this is what's usually done. You have the code, you write some test, and then you need to explore all these different interleavings that you have that could potentially lead to different results. So the issue here is that these failures can be triggered only by some specific schedules. So it's difficult to explore these schedules. This state space is usually very large. So you need very sophisticated analysis to do that. Indeed, most research has focused on that, on exploring the schedules for this. A lot of good work here from Microsoft, folks who have worked on chess. People from Berkeley have worked on active testing. I thought that in the next talk that Koushik will be talking only about active testing, but actually I just learned from him that he'll be also talking about other things. But let me just say what most of this existing work focused on. Basically, it was this thing that someone somehow wrote the test for the code, and you have one code version, and now what you need to do is to explore these interleavings to find whether there is a bug. And there are a lot of techniques that are proposed for doing that. But there are many other problems that we have in testing multi-thread code, especially if you want to unit test this code. So there are issues how to write these tests. I said most previous research just assumes that the test somehow exists, the developers wrote it manually, but it's not clear how people can write that. Especially in the cases where you do want to encode certain expected result that does depend on the schedule. How do you express this specific schedule for which you want to encode the result? Then the next thing is how to explore this test, especially when the code evolves. Again, as I said, most of the previous research focuses on analyzing only one given code version. But as we know, code evolves over time. People make changes, correct bugs, add new functionality. So in the context of sequential code, there has been a lot of work on this regression testing. How do we make testing better as the code changes? How do we make it more efficient? This was not addressed widely in the context of parallel code. And then there are also the issues of how to automatically generate some of these multi-thread unit tests, how to generate the test code itself, and how to generate schedules. These are some of the challenges. There are obviously others, but I picked those ones that we worked on. So we do have work at Illinois on all of these three topics. And what I'll spend the most time on today will be on the first topic of writing these multi-thread unit tests. basically how do you manually write tests, especially in the cases where you want to say that the result does depend on a certain schedule that is taken. So we've developed a tool that we call Immunity, or IMUnit, Immunity, for improving this testing. We've also done the work on these other two topics. So one is this regression testing. Again, the idea is I test my code once. Now I go and make the change in the code. Typically, the change that I'm making in the code is quite small, whereas running this testing takes a lot of time. The question is, can I make my testing faster if I just focus on the change? So we've developed some techniques there for doing this test prioritization, test selection, basically building on some very successful results from testing sequential code. And then one of the issues also that I mentioned was automatic generation of tests. So we had a recent result on that, something we call Ballerina. Can automatically generate the code and check for some parallel bugs. And there has been also a lot of other work by the colleagues in the department, some of them through UPCRC and I2PC. Madhu Parthasarathi has done a lot of work with the Pennelope and Exceptional and a few other tools and approaches, testing atomicity violations and looking at other problems. Grigory Roșu has done a lot of work with the JPredictor and Java MOP extensions for concurrent code and so on. But I won't be talking about that because I don't have time. So what I'll focus on will be this, the immunity. This was a project not only funded through UPCRC, but we had some other, NSF and NASA, NSA, Samsung, and so on. It's a part of a broader project on trying basically to make this parallel testing for parallel code easier to be adopted into the whole software development process. Some people have worked on that. Vilas was the senior student who was leading this, a few other students, and then Grigory and myself. But let me get to the technical things. So here's the example of this thing. Let's say we have a certain class that we want to test. This comes from some open source course from Google. Let's say we have this class, the concurrent hash multiset. It's basically a collection where you can store objects, and you have operations like add, remove, count. And what you would like to do is to write the tests for this particular class. So let's say we want to test a certain scenario where we have two threads that execute. So they operate on the same shared object. One of them does two adds, and the other thread does a remove. And what we would like to do is to test whether these add and remove and count do behave as we would like them to behave. Now, the issue here is that the value of this count is schedule dependent. Based on the order in which we execute these add and removes, based on the order in which even the instructions from them interleave, we can get different results. For example, if you execute in this scenario, what should be the count of 42? 1. Oh, OK. That was the answer 1. I thought that was a hand up. OK. So the answer here should be 1, because we add it, then we remove it, and we add it again. The question becomes, how do we encode in our scenario that we want this particular schedule? Now, notice here that we are not doing here interleaving of methods. I just even want to say they just need to be executed atomically. So what we've seen a lot in the open source is something that's bad. Don't do this at home. But this is what people do. So they use a lot of these sleeps. They basically say, I'm going to start 2 threads. This is the actual Java code. This is starting 1 thread. This thread does 2 adds. There is another thread going on here. This one does remove. And then in order to ensure that they are getting this order, or rather, in order to attempt to get the specific ordering of the events, they add these sleeps. This basically says, wait for 40 milliseconds. Meanwhile, I hope something else will finish. And I'm going to here wait for 80 milliseconds and do this. So as you all probably know, there are a lot of problems with these sleeps. Kind of not the best way to do that, but we've seen that people do this a lot. So some of these problems include that these tests are fragile. And what I mean by that is the following, that even when you put these sleeps, you're not sure that you're going to get the result that you want. It may happen that the actual Java virtual machine does not execute the schedule that you intended. So you may get into this situation where the test seemingly fails, even though there is no bug. So the test did not fail. You may get here, say, 2 or 0, not because there is something wrong with your remove or add, but because these did not execute in the order in which you wanted them to execute. So in order to prevent these problems, people usually put these bounds on sleeps that are very long. Let's say, wait here 40 milliseconds, probably 10 would be enough. But just to make sure that you get the schedule that you want, you wait longer than necessary, and then you get inefficient tests. You also get tests that are non-modular. Namely, if I have two very similar tests, I cannot combine them. I cannot reuse that code because I'm sprinkling these sleeps all over, and I cannot reuse the sleeps. What I want to reuse is this thing, that I have these adds and removes. And then the schedule is very, very implicit. If you try to understand what this test is doing, what is that it's encoding, it's kind of very hard to figure what's going on. So others have also recognized these issues. So there have been a few research proposals how to address these things, this Conan, ConcJ, unit thread control. The latest solution before ours was something called Multithreaded TC from Bill Pugh and his group from Maryland. And it addressed some of the problems from these sleep-based tests, but not all the problems. So we've then proposed our solution, which we call this immunity, which we hope makes these things easier to solve. So here's how immunity test looks like. Basically, instead of writing those sleeps that I had there, what we do is write these events. We say there are certain events that are happening in the execution. And then we write this schedule that says what is the ordering that I want of these events. Basically, what I'm saying here is that I want this add to finish before I start this remove. And then once I finish the remove, then I want to start this add too. So I insert these adds, and then I add that schedule there. Now, this makes this test robust. What I mean by that is once I write this schedule, there is certain execution engine underneath this that's going to ensure that the code actually does execute in the order in which you specified. If the Java virtual machine wants to execute in a different order, then it will start kind of stopping certain threads to ensure that you get the actual order that you want. As we'll see in the experiments, they turn out to be even more efficient than the sleep-based tests. They're modular. This is something I did not show, but basically you can reuse the schedules from different tests if you want to have different scenarios. There are actually two schedules up there. And the schedule is very explicit. So if you need to understand what this test does, if something fails, if you need to debug, if you need to change these things, it's much easier to understand.
Question?
Yes?
Code a deadlock or something bad in your schedule?
Yes, it's very, very possible. We have both static and dynamic analysis to try to help with that. First here, when you encode the partial order of the events, you can just introduce the cycle. So you just do something wrong. Let's say there instead of 2, you put 1 by mistake. So we can statically find some cycles. But people usually don't have too many of those. What does happen often is dynamically, as you run this code, that the schedule may be unrealizable. And then we can detect whether this is happening because of the deadlock in the code under test, or because the execution engine got stuck here waiting on certain events to happen. Then we can give appropriate warning or error message telling you that you're having this problem. OK, so to see how expressive this language is, so we got about 200 tests, these sleep-based unit tests from open source Java code from various projects. Then we translated them into this immunity by adding these events and orderings. And we found that we were able to express almost all of them. One issue that we did not support, though, is the event in loops. So we cannot actually use this immunity thing as kind of general purpose programming where you would enforce ordering between events, because we do not allow events to be repeated. And the reason was that simply we did not need that for tests. If you wanted more expressive language, that's something we consider as a future work, but it will just going to make the language much more complex and potentially less likely to be adopted because of that. We also measured the speed of the execution. So what we found was that we were about 3 times faster than the sleep-based tests across all of these 200 tests, where you run with the sleep, with the bounds that the developers put, versus running with our engine. And the issue here is that simply these sleeps are inefficient besides all the other problems that they have. So basically, just summarize on this immunity. So it's a way to write these multi-thread unit tests. The currently dominant solution kind of in practice is using these sleep-based tests despite all the problems that they have. So immunity addresses those problems, and this schedule language is expressive, and our execution is efficient. We have also a tool to help you migrate from these old traditional sleep-based tests to the new things. More details are online in the paper, in the tool, so the tool is publicly available. We had some people who downloaded, they send us bug reports. On one hand, you can view that as bad, like, our code has bugs. On the other, you can view that as positive. Someone is using our tool, and cares enough to submit a bug report. OK, so that was about immunity. I'm just going to skim in 2 minutes through 2 other projects. So one of them is this change-aware preemption prioritization. So the goal of immunity was just write tests. The goal here is, as my code changes, how can I make my testing faster? So basically, here is the idea. I had the code, parallel code. I have test. This testing here takes a lot of time. As the code changes, the change is typically small. Can I somehow exploit the knowledge of this change? Can I statically analyze this change and exploit that to optimize this process here? And what we found that this is indeed possible. Here's a comparison for using this change-aware prioritization. Basically, if you have something that understands what's changed in the code versus just doing exploration that does not understand that. And so what this shows is the speed up that we obtain over this change-unaware prioritization, kind of as the base case. In some of the studies, we use chest. In some others, we use some other exploration approaches. Some of the things we sometimes obtain the speed up of 5 times in this testing. This for various stateful and stateless exploration. Sometimes we obtain 2.7. There was only one case where we were slower, basically, where our approach was slower than the default. So overall takeaway message here is that there are ways to make regression testing faster for parallel code. And then the last thing that we did most recently was this about automatic generation and clustering of this unit test for multithreaded code. So rather than manually writing some of this to try to automatically generate. And basically, we call this technique Ballerina. So what it does, it generates these tests that use random generation to find kind of randomly here what methods to put. So it generates some complex prefix, generates potentially complex objects. In the example that I had with that multiset, I showed relatively simple things, but it can generate more complex things and then run some methods in parallel to try to find bugs. So the good thing here was that we could find bugs. Maybe potentially bad thing was that we find too many failures. So we had some clustering methods that help us to identify which of the problems are likely due to the same root cause. So evaluate this on some known bugs. We found that this approach worked better than some other baselines. And we also found some previously unknown bugs. So basically, to summarize, we have a lot of work going on testing for parallel code at Illinois. I'm just presenting some of the work from my group on this immunity and then this regression testing, test generation. There are other colleagues who work on other things. OK?
Any questions?
What about measuring coverage, right? In order to really understand if testing is good enough, then you need to have some measurements of coverage.
OK, that's a very good question. So the question was, can we measure coverage? And we did not look into that, but there is a work on proposing various coverage criteria, how to measure maybe interactions, these shared variables. Did you cover certain interactions about that? You cover certain locks, contention on the locks. First, even defining the coverage criteria for parallel code is unclear how to do. But yeah, this work, we did not do that. Yes?
Back on the immunity work, writing that test, it actually seems pretty hard to read. Why couldn't you just write the thread, the 2 things in a lead?
OK.
Instead of putting the markers and then having the, it seems like it's difficult to read.
Sure. So you mean you would more want to write it the way it looked like on a slide, right? Kind of the way this way. Yes, so that goes back to the, how can I have, an integrated development environment that would let me visualize my code in this way, right? If I write one thread here, one thread there, is there something that will visually spread these things and do that?
Just syntax. Yeah. Describe a thread. This is for thread 1. This is for thread 2.
Sure. Yeah, one can think of those ways how to do that. Yes?
This is a question for anybody who builds a debugger. It seems like if we're going to teach parallel computing online and do auto-grading, having a debugger that automatically looks for race conditions in the submitted code would be a very useful tool. I'm wondering, is anyone ripe enough to use for that purpose?
So here we did not really focus on trying to find bugs. This is more like you encode your test once you run this, you still need to use some other tools to look for these bugs. But yes, if you have students' code, you likely need to run the tools to find the bugs. Actually, you can just skim through the students' code most time and just find the bug. I mean, okay, well, it gets harder. Sure. If you have, massive cores, then you need to run some tool to look for these bugs. Yes?
So when you're unit testing, I think a better assertion at the very end would be something like, count is either 1 or 2. And whenever it is 1, whenever it is 2, it so happened that the remove executed before the two acts. Right? So what you want to say is some assertion that captures behaviors of all interleavers as opposed to one particular interleaver.
Okay, so that's a very good comment. So the suggestion is that rather than writing, I want to get exactly value 1 in this particular schedule, the suggestion was, why don't I say here that the value is 1 or 2? So if I just say the value is 1 or 2 without saying under which schedule, then I can be missing bugs, right? So if my code always returns 1, that would pass.
If it returns 2, it so happened that the remove executed before the 2 acts, right? So essentially, I want to write assertions over all possible schedules.
That's fine. You can actually do some of that in Unity. Unfortunately, that's not shown here. But you write assertions that actually say for which of the schedules you're getting which of the results. You do not need to write only one schedule. You can have a larger number of these schedules, and then you can encode, a set of the results here. I mean, the limit, you can try all these, linearizability, try all possible orderings, just encode that you're going to get one of those under certain conditions. And these events need not be only here in the code under test. You can actually put them in the test code. You can put them in the code under test, sorry. They need not be only in the test code. You can put them in the bodies of these methods such that you get their interleaving, such that this is not executed atomically. Is there one more question here? Or?
No, I think. No.
Okay.
Thank you very much. So now we have Dany Dig. And okay, he's going to talk about annotations, I believe.
Refactoring. All right, so I'm Dany Dig. I'm a research professor at the University of Illinois, where I lead the area of software evolution. And especially, I want to give more of a higher level talk on my past work on software evolution, my current work on software evolution, and I will conclude with my future work on software evolution. Of course, I will put more emphasis on the work that has to do with parallel programming, but I've done much of other works that have nothing to do with parallel programming, but regardless are still very useful. So this guy here, it's a famous Greek philosopher. His name is Heraclitus. He's famous for many things, among others this quote, that change is the only guaranteed constant. Now, this is no news for us who are using software every day, because we know that the only software that remains successful is the software that constantly changes. And here I have an example of changes. So people add more features. Microsoft constantly pushes more features, new versions. Windows 8 comes now. People add fix bugs, improve performance, improve security. And in fact, the only software that doesn't change is software that is dead and nobody uses. So here are some visual reminders that our software changes. This is from just look for updates on my Microsoft Office. And apparently, Office 2011 has a bunch of updates, and some of them are critical, so probably I should go and apply them. Now, here's another visual reminder. So Windows 7 also has a bunch of updates for me. And I see that several people here are also using Macs. So if you're using Macs, this is another reminder that also Apple has lots of updates for you as well. Again, these are reminding us that our software constantly changes. So programming is all about changes. How can we manage and how can we express changes in large, complex, large code bases? So we need to change the way we program to better support this changing ecosystem. So I view programming as program transformations. Programmers take version n and they create version n+1. Now, how do they do that? So this is one of the research questions that my group addresses. What are the kinds of changes that occur most often in practice? And second, how can we automate them to improve programmer productivity and the software quality? So answering these questions is not only very valuable for the practice of software development, it's extremely rewarding and challenging also intellectually. Here is a very high-level overview of my work on automating these successfully automating three kinds of software transformations. So for my PhD dissertation, I've been working on how can we upgrade clients of a library API to move from version 5.2 to version 6.9 or whatever. I've also been looking at the area of software testing, which is I mostly collaborated with Darko on. Well, it's not only that the software under testing or the production system changes, but when the production system changes, you also have to change all these regression test suites. You have to change the assertions. So how can we automatically also upgrade the test suites? Of course, the most recent, my work has been in the area of how can we change sequential software to embrace parallelism and to retrofit parallelism. And of course, this is a very hard problem, and I do not believe in full automation. I rather believe in an interactive approach where you use the smart brain of the programmer to guide the tool, and then the programmer exposes to the tool, this is the kind of transformation that I want to do on my code. The tool is going to check, is this safe? And if it's safe, then it applies the transformation. So this is not fully automatic. It's an interactive. It's driven by the human brain. More than the number of publications, I'm very, very happy to see a real-world impact of my work. So I've been developing the first open source. This is the world's first open source refactoring engine for Java. This was developed as a plugin for JEdit. JEdit used to be the #1 IDE 10 years ago. Some of my other work that is in the area of software upgrading is shipping with the official list of the Eclipse. So Eclipse is the #1 development environment now for the Java developers. It's used daily by millions of Java developers. Some of the other work that I've done here doesn't ship with the official list of Eclipse, but it's standalone plugins, but it's still widely used at several companies and several research institutions. So it's used widely at Google and other big, large companies. Here in the area of software testing, one of our tools, ASTGen, is used in the testing infrastructure at Sun NetBeans, where they test the NetBeans ID. Actually, right now it's no longer Sun. This should be Oracle. And of course, the most recent work on refactoring, interactive refactoring for retrofitting parallelism, it's going right now into the official list of Eclipse. So if you are using Eclipse Juno release, which is 4.2, some of this work is going into 4.21, which is coming at late August. So I do not have time to talk about all this work. This is just a one slide, very high-level overview of our interactive refactoring for parallelism. So we are supporting all kinds of changes that people find practical and they need in the practice of converting their sequential code for parallelism. We have one category which we call enabling transformations. These are transformations for thread safety. They do not introduce multithreading. They just take your code and prepare it for multithreading, so make it more thread safe. One example of this is making a whole class immutable. So if I'm changing the class so that all the instances from this class, I can never update and never change the state once I instantiated this class. Now this class is what we call embarrassingly thread safe. I can share it with all my threads in the world, and there is no need for synchronization. Here we have refactorings from the second category. These are actually refactorings to introduce multithreading. So here we have one that introduces the parallel recursive divide and conquer 4 joint task parallel pattern that Tim Hudson has in his book and in OPL. So we have one refactoring, and this is one of the refactorings that goes in Eclipse 4.21. And also we have another one, loop parallelism. This is converting sequential loops to parallel loops, again, via a refactoring interactive approach. We have a third category of refactorings. These are the ones that you want to apply if you added some locks or some other heavyweight synchronization mechanism in your code. You want to make your code more scalable, so you want to get rid of this and replace them with more scalable constructs like these atomic packages that use underlying, under the hood use compare and swap hardware instructions. So Java has them via the atomic package. The C# has them via the interlocked constructs. I forgot how it's called in. TBB also has something called atomic, so it's the same construct. We always, as an approach, as the way how I'm developing and how I'm conducting research, I always validate empirically. So we validated our refactoring tools by running them against hundreds of files from open source projects and also doing controlled experiments with programmers. And we found out that these kind of tools dramatically improve programmer productivity. It's much, they are fast enough, even though they do very complex and very intelligent program analysis, which require interprocedural pointer analysis on, to figure out what's shared through the heap. So these are still very fast. It's fast enough that actually programmers can use it in the interactive environment, in an interactive mode. We found out that unlike the open source programmers, our tool applies the transformations correctly, whereas open source developers apply them incompletely, so they probably carry out 9/10 out of the refactoring and left 1/10, and exactly that 1/10 left it's a bug. And of course, there is a good motivation. So once we refactor this code, they exhibit good speed up. Dany, who is the Java #1 lead architect of the concurrent package in the Java standard libraries, writes on the mailing list that he was very impressed with one of our tools with Looper. He says that I expect it will be useful to just about anyone interested in exploring these forms of parallelization. Well, it's not only that we develop these kinds of tools and we put them into the hands of the programmers, but I believe that if you ship them as a plugin for a widely used development environment, they are much, much more likely to be used. If you want to really impact the lives of millions of developers, that's the way to ship and to package your research. So the tools that we presented so far are all developed as plugins for Eclipse. Now we're starting to work on plugins for Visual Studio, but that's the next slide coming. You can download these tools free, open source at refactoringinfo.tools, or you can wait for another 5 weeks, and you can download them from the official list of Eclipse. So if you do the Eclipse Juno release, the minor release #1, some of these tools will be integrated in the official list of Eclipse. This is very exciting. On the educational side, we have this successful summer school. So I educated more than 800 participants who come to these summer schools on this topic of refactoring for multi-core parallelism and on the topic of multi-core parallelism itself. So we just finished last week our 4th summer school on multi-core programming in Illinois. And this was very successful. We had some high-profile keynote speakers, the caliber of Dany and Cliff Click. And I also do 1-week training courses. So I've done 3 of them in this area. And when I come to Seattle, and I either come at Boeing or I come at Microsoft. So Boeing is very interested in this topic. So apparently they are interested enough to hire me to teach these 1-week programming intensive exercises and these training courses. Also do tutorials at big conferences like UPSLA or ICSM. And more than this, actually, we have another metric. So there are actually people out there who care enough about tools. So they not only download and use our tools, but they bother to send us a bug report. So we are humans. We make mistakes, and our software is no different. So all the tools that I presented so far, I know that they have some bugs. We are fixing those bugs. We are making them more production quality. And apparently some of them are good enough that Eclipse Foundation has integrated them in their official release. So here I want to talk about some of the current and ongoing work. So I looked at the industry trend, and I saw that the industry has this trend of converting the very hard problem of using parallelism into a slightly easier problem of using a parallel API, using a library. And Microsoft has these libraries, TPL, peeling. Intel has these threading building blocks. And there are many other libraries out there. Yet we know very little about how do programmers actually adopt these libraries in practice. We know very little of how can they find examples, how can they educate themselves on how to use these library APIs. Some of these APIs are overly complex. Some of them are very rich, so they expose several overloaded methods with several arguments. Yet programmers have very little examples and very few examples from the real world. So also library designers, if they don't know about how people use this in practice, they do not find examples of misusages. They don't know what's tedious, what's error-prone. Researchers can make wrong assumptions, so you can build a data race detection tool thinking that people only use logs. It turns out that from our study, we found out that actually logs are just one construct. There's a long tail of many, many other synchronization constructs. So we analyzed all the open source projects that we could find in the CodePlex repository. This is Microsoft CodePlex repository and GitHub. These are the very widely popular repositories. So we analyzed all the projects that use Microsoft TPL and peeling libraries. This is about 70 million lines of code contributed by 1,600 different developers. And this is the first in-depth, large study at this scale of how do people in the wild, how do they adopt these parallel libraries. So some of the findings that we discovered through this study are quite interesting. For example, we found out that indeed open source developers embrace and adopt parallelism. So we found that 37% of all the open source projects in the GitHub and CodePlex ecosystem use some sort of multi-threading, and out of them, 74% use multi-threading for concurrency, for improving responsiveness, and About 39% used multithreading for improving throughput and for actually squeezing parallelism out of their code. We also found, very surprisingly, that in 10% of the case, developers' code, they think that the code runs in parallel, but in fact the code runs sequentially. But just a very small, minor syntactic mistake that they made in their code. Also found out the developers make their parallel code unnecessarily complex. So this is what we know from software engineering. We call this accidental complexity. Now, parallel programming is hard, but they make it unnecessarily hard. This is the first large-scale research project. We could only do this because Microsoft has this new infrastructure called Roslyn. So it's an analysis infrastructure for Visual Studio. And we were, for a while, and I think we are still the ones who are actually pushing it to its limits. So we cranked, when you crank this on 70 million lines of code, you push it, you push this tool to its limit. And of course, we found lots of bugs. So we reported more than 20 bugs to the developers. They were very keen on acknowledging and on fixing those bugs. So in the recent release that just came out last week or so, Roslyn is much more robust now. And one of the things is, how do you report bugs without actually cutting down bridges and without losing friends? And apparently, we managed to report more than 20 bugs in the Roslyn environment, and we're still very good friends with them. So some of the implications, so this is good news for developers. So we have this website, learnparallelism.net. The reason why it's called .net is because it's for .net. Here you find thousands and tens of thousands. If you're a new developer who has just heard about, OK, I can do a parallel for in C# in TPL, you can look at this website and you can find tens of thousands of examples of how other developers in this more than 600 open source project use parallel.4 or any other constant you care to learn about. This is good news for researchers because now I can make more informed decisions on what are the kind of research tools that I want to develop. Of course, it's good news for library designers because Stephen Tube, who is the lead architect of TPL, found this study very useful, and this is going to influence the future API development of the TPL library. So since I'm in the Microsoft ecosystem, I thought, well, Microsoft was nice to me, so gave me another grant to keep working on Microsoft technology. So I started another project, this is very recent, on refactoring for spreadsheets. So the surprising thing is that the number of spreadsheet end users, these are people who call end user programmers, this is estimated to be at least 100 million. Now this is very, very, it's very conservative. The number could be way much larger than 100 million. But anyway, this gives you a sense that at least an order of magnitude more end user programmers than professional programmers. Well, what does it mean practically? It means that the number of bugs that end user programmers create is at least an order of magnitude larger than the number of bugs in professional software. And when we looked at thousands of spreadsheets from the real world, we found out that indeed they are riddled with the same, they are plagued with the same smells, with the same errors, with the same mistakes that professional programmers make. So lots of hard-coded expressions, duplicated constants, accidental complexity. So these have effects on both the performance and also the future maintainability of the spreadsheet and the workbook itself. So we developed RefBook. This is the world's first refactoring tool for Microsoft Excel formulas. And right now we are supporting 7 refactorings. Here's an example of one of them. So you can look in a table. You can extract a sub-expression from a complex formula and extract it in its own column. And then the tool itself will go and find some other instances of the same sub-expression in other columns and replace all those instances with the new column that you just extracted. So now if you have to change your table in the future, you have to change that sub-expression. You just go and change it in one single column. You don't have to go and hunt all these other columns that previously were duplicating the same sub-expression. So like with any other tools, we always evaluate them empirically. So here we've done empirical evaluation from 3 different angles. We look at a survey and controlled experiment with 28 Excel users, and also look at a case study where we looked at 4,000 spreadsheets from the real world. And we found that users prefer the better readability and the nicer maintainability of refactored formulas. We also found that our tool, of course, as you expect with tools, they are faster and more accurate than doing these changes by hand. And we also found that these refactorings are widely applicable because in those thousands of spreadsheets, as I said before, they were riddled with all kinds of smells and all kinds of problems that could be fixed through refactoring. So I want to conclude with, Apparently, I'm presenting the wrong version of the slides. What happened here? Oh, so this is a recover file. This is the recover file. This is not my. Whoa. Okay, this is surprising. I noticed that one of my bullets was empty before. Okay, let's see. Okay, that's because I used Mac. No, it's because I closed the lid so that the lid wouldn't bother you. So probably that crashed Microsoft Office, and it recovered this. Anyway, what I wanted to say here. Okay, apparently I moved it somewhere. Okay, so I'll just end up with this slide. I had one more slide, which in my deck of slides is nice and polished, but apparently the version that Office recovered just doesn't contain all my text. So we are starting and we are developing and inventing the next generation of development environments. This is a large project funded by under SHF, large program funded by National Science Foundation. We are inventing a new generation of programming environments that treat software changes intelligently. So we are enabling programmers to actually author and to script their own transformations. You'll be able to reuse them in other contexts. We are enabling a version control system to show the history at a higher level, so it makes it easier to understand the changes. Of course, we are inferring these higher level changes from lower level changes. So I think this is going to significantly and drastically change the ecosystem of programming environments. And of course, it will be good to see some of these things going into Visual Studio probably in a few years. So that's all that I had to say.
Thank you very much. So we are running a little late. Probably if you have questions, please see Dany during lunch. We are now going to have the presentation from Koushik Sen, Active Testing and Concurrent. Joseph Torellas reminded me that Koushik came from the University of Illinois, and he just got tenure from UC Berkeley. So this is another example of great collaboration between the two schools.
Thank you.
Tech transfer.
Brent. So today I'm going to talk about Concurrent, a domain-specific language for testing concurrent programs. And this is joint work with my student Jacob Burnim, Typhoon Elmas, my postdoc, and my colleague George Nekula. So so in the last few years, there has been a significant amount of progress in automated test generation for both sequential programs and concurrent programs. And I was in fact involved in a couple of those projects. And what I noticed in the last few years that there is a very slow adoption rate for this kind of techniques in the industry. And programmers are not willing to use these automated test generation tools. And on the other hand, if you look at tools like JUnit, XUnit, and so on, programmers use them regularly and they're very popular. So we started thinking about developing a similar kind of XUnit tool for concurrent programs. And we came up with this idea called Concurrent. And there are some other tools that you have seen, like Immunity, and there is a tool developed by Bill Pugh, so it's in the same spirit. So, suppose this is, so I use this SpiderMonkey JavaScript engine as a running example. Suppose you want to test this code. It has 121,000 lines of code, and it is used by the Firefox browser. And you want to test certain functions in this code. Okay. Now, it's easy to write a sequential test for this code. You just write a function, harness function, and you fix the inputs, and you call the methods that you want to test, and you check the output. And one of the nice property of this kind of unit test is that if you run it multiple times, you get the same outcome. Either it will fail, or it will say that the test passes. So this is a determinism property of a test, and it's very desirable. And we get this kind of deterministic behavior for tests written for sequential programs. Unfortunately, if you want to do a multi-thread testing or concurrent testing for this program, then you create several threads and you run this code in parallel. But if you write such a test for concurrent program, you lose this property of determinism because the threads can interact with each other, and you may not get the same output if you run it multiple times. Okay? Now, so that is the key problem why there has not been any successful tool for unit testing of concurrent programs. Now, what people use in the absence of such unit testing tools for concurrent programs, they do stress testing. The idea is you create numerous threads, thousands of threads, and you run the program for several minutes and see if something bad can happen or not. Okay? And this is what people call stress testing, and it's really used in practice. Another set of approaches that people have developed is called model checking. It's mostly in the research area where you try to explore explicitly all the schedules of the thread and see if there is any bug. The problem with model checking is if you try to apply it to real world code like say Apache or Firefox, it's very hard to scale because there are too many, the state space is too high. Moreover, you have to have total control over all possible sources of non-determinism if you are trying to do model checking, and that is not realistic for real software. Okay? And also we have seen that many times programmers want direct control over the scheduling and the test that they are trying to write. And if we can incorporate the programmer's insight in the test, then our testing could be more effective. Okay? Another alternative that people have explored and which is surprisingly the most used approach to test concurrent programs is to insert slip statements, as Darko showed. And if you look at the bug databases for various kind of concurrent software, you'll see that most of the bug reports include slip statements. And the idea is you create a number of threads, but also you put the slip statements at the right location so that you can play with the schedule and you can reproduce the bug. And the reason behind the success of the slip statements is that it's very lightweight and convenient to write this test using. But it's, on the other hand, it's not formal and it's not robust. You might see the bug sometimes, you may not see the bug other times. So what we wanted to do, we wanted to come up with a testing framework that is as lightweight and convenient as slip statements, but at the same time which is formal and robust. Okay? And that was, Concurrent is the result of that. Here is the, so I'll give you a tutorial introduction to this Concurrent using this benchmark, the SpiderMonkey JavaScript engine, which crashes on some execution used with an assertion failure. And here is the bug report that was filed by some user to the bug database. And as you can see that he tells us there is some kind of schedule involving 3 threads and some unknown schedule between 2 other threads. And if you take that particular schedule, you'll hit the assertion violation. Now, our question is how can we take this kind of programmer insight and translate it into a very small test script so that we can make this bug reproducible. Okay? And here is what we do in Concurrent. We take this user insight and ideas about the thread schedule from the programmer, and we write a test in our DSL, and then we run the DSL along with the software and the test and systematically explore all and the only thread schedules that are specified by this DSL and see if we can reproduce the bug. And I'm going to describe how the DSL looks like. And here is how it works. The software under test, we instrument it, and it generates events in a similar way as Immunity does. But whenever it sends events, it gets blocked by the Concurrent DSL. And the Concurrent DSL, based on its logic, it unblocks the thread from time to time. Okay, so let me show you how a Concurrent test would look like. The bug you have seen, it says that it mentions that you will see the assertion violation if you schedule 3 particular threads in a particular way. Okay, so we definitely know that the bug is happening due to 3 threads. Okay, so let's try to first write a test that will see if the bug is due to concurrency or not. So here is our first test script, which says that pick any 3 threads in the program and run them sequentially until they terminate. Okay, And this is what we do in this test. We pick TA, TB, and TC for 3 distinct threads. And while they're running, choose a thread and run them until the end. Okay? Now, this is a test that we write in our DSL. So this is very easy to understand. It's an embedded DSL in C and C++. So you don't have to learn a new language to write this kind of test. You have to understand a few constructs that you have provided. And once you have written the test, we'll run it along with the software under test. And we'll explore 6 schedules in this case, 6 possible ways of running these threads. And we see that there is no assertion violation. And at this point, we know that the bug is not due to, the bug is definitely due to concurrency. Okay? Now, we need to refine this test so that we can actually reproduce, create that particular schedule and hit the assertion violation. So we write our next test, which will try to explore all the schedules of the program. And that's what we exactly do in case of model checking. Okay? So here is the second test that we write. We just change one line in our test, which says that run thread until read mem or write mem or some other event. Instead of saying that run thread until ends. Okay? So this means that interleave these 3 threads in all possible ways and explore the entire state space. Now, this is a good test. This actually finds the bug, but it's like model checking. We end up exploring like more than 1 million schedules, and it runs for days, and eventually it finds the bug. Okay? So, and also in this process, we learn something that if we write this kind of test, you have to take control of all the possible sources of non-determinism in your code. Otherwise, you cannot guarantee systematic termination of your search. Okay? And moreover, since you are instrumenting all possible instructions in your code, it's too heavyweight, and you spend a lot of time searching schedules which are not important for the bug. Okay? So we came up with this notion called tolerant model checking, where we say that it's unrealistic to instrument all possible sources of non-determinism in your source code. So why don't we allow the programmers to specify the non-determinism that matters for the purpose of the bug and control them? Okay? And also, why don't we provide mechanisms so that we can constrain the search, so that we can say that only interleave the threads within these 2 functions. Do not interleave the threads all over the places. Okay? So these are the 2 things we provide in this concrete DSL or this concurrent framework. And and also in this framework, if you wish to do model checking, you can write your own heuristics, which can be full model checking, or it can be context-bounded model checking and other heuristics. So let me show you how we can localize the search and only specify the non-determinism that we are interested in. So if you look at the bug report again, it says that the bug happens only when the 3 threads are executing the JS destroy context. 2 of them are executing the JS destroy context, and 1 of them is calling the new context. Now let's try to encode it in our test. And here is our test. We modify again 2 more lines. Here we say instead of waiting for the thread until they enter the JS new context, we also make the thread T and TB wait until they enter the function JS destroy context. And then we try out all possible interleaving between these threads. Okay? So this is a much restricted and localized search. We do not start the search as soon as we create the threads. But once we have entered those particular functions, we start the search. Okay? Now, if we so this is how the tree looks like, the model checking tree looks like. It first takes a very particular specific schedule, and then it tries to search the interleaving space. Now, if we write this test, then we can actually hit the bug after exploring 50,000 schedules, and we see the assertion failure in a few hours. Okay? So this shows the power of concurrent. In order to write a concurrent test, you don't have to control all possible sources of non-determinism in your code. You can just specify the non-determinism that you want to control and keep the other sources of non-determinism uncontrolled. And the concurrent test can still do systematic search. And if at any point the systematic search fails because the fact that you have not you are not controlling all uncontrolled non-determinism, it will raise a flag. And at that time, the programmer, what they can do, they can either make the test more robust by putting more non-determinism, or they can continue the search and not expect any soundness guarantee. Okay? So this is the idea. And finally, 50,000 schedules are too high. So we looked at the exact thread interleaving, and we tried to further localize it. And it turns out in the bug report that it tells us where to exactly interleave the thread so that we can create the bug. And we incorporate that knowledge further into the test by adding 3 of these lines. And if we now run the test along with our software under test, we actually hit the buggy schedule within 10 iterations. Okay? And so after refining the test, we had a better understanding about the bug, and we knew exactly why the bug is happening. So we finally came up with an exact schedule of the thread that actually leads to the bug. And this specifies a single schedule. You don't have to do a search, and you can run it, and it will hit the bug on the first schedule. Okay? And note one thing, this is not like specifying the entire schedule of all the threads. We are only specifying the key scheduling decisions that are important for producing this bug. Now, once you have this test, you can put it as a regression suite in your test, and it's kind of robust to code change. If the code change, it will still run, and it will be able to find the bug if it's still present. So this is a brief tutorial of the concurrent framework that we have developed for testing concurrent programs, where the programmers get better control of what they want to write and how they want to control the schedules, and play with the various kind of model checking, heuristics, and also search techniques. So we have implemented this tool in an embedded DSL for C++, which is available. We can write both unit test and system testing. And for unit testing, we run it in the same process, and we do both manual and automated instrumentation. And for system testing, we run it as a separate process. So I guess we are running out of time. So just to give you an idea, as I mentioned that most of the model checking techniques do not scale, but we managed to run it on very large software, including the Mozilla JavaScript engine, the threading library, the Memcached, Apache H3 Surfer, and MySQL, and we managed to actually reproduce a number of bugs that has been reported in the bug database in a robust way, and the tests are like 5 or 6 lines of code, and that was a big success for us. Okay, thank you.
Thank you. So if you have more questions, Koushik is going to be around for lunch, and now we are going to have the last presentation by Suni Chatterjee from Microsoft, and he's going to be talking about fighting concurrency bugs with advanced static analysis technology. And after his talk, we will have lunch. Food is going to be in the back, behind this wall. And then we are continuing with a session on applications from 1 to 3. So at 1, please come back here, and we'll continue with the session. Thank you.
Hello, everyone. My name is Suni Chatterjee. I am a developer in the analysis technologies team in Windows. And today, I'm going to talk about a set of concurrency tools we have developed based on static analysis that we use for finding and fixing concurrency bugs in major softwares in Microsoft, like Windows, Office, and other divisions. I know we are running short on time, so I'll be as brief as possible, and so that you can go for lunch. So first, I would like to talk about our team. We are part of the engineering desktop team in Windows. We develop and support some of the most critical program analysis tools and services that are used across Microsoft. We have various tools at the source level and binary level. At the source level, we have a set of global analyzers, local analyzers, and we have a source code annotation language called SAL. At the binary level, we have binary instrumentation tools, and we have code coverage tools based on the binary instrumentation technology. Today, specifically, I'll be talking about a concurrency SAL, which is a source annotation language we have developed for specifying locking behavior in a program. We'll also talk about a toolset called EspC. EspC stands for Extended Search Over Programming, and that finds concurrency defects, which can also understand SAL. We will also talk about how we are using these tools internally in Microsoft to find and fix thousands of concurrency bugs at compile time on the developer's desktop, and how we are planning to ship these tools externally so that we can help the ecosystem. So we are all aware of the common locking problems that we see every day. There are insufficient lock protections which result in race conditions. There are lock order violations which result in deadlocks. We forget to release locks resulting in orphaned locks. There are no suspend guarantee violations. There are APIs which have an implicit blocking nature like send message, and we inadvertently call them without realizing that they might have a potential to block our application. There are many similar classes of locking problems, and our tools try to find and fix these problems at the developer desktop. So the key challenge for us is how do we enforce the locking discipline? Because we all know that locking discipline is essential for avoiding multi-threaded errors. However, it's surprisingly difficult to enforce in practice, and there is no support in the high-level languages like C, C++. So our solution is a set of concurrency tools that is based on annotations for locking rules. Annotations are a formal way to make implicit assumptions about the locking behavior explicit. We then have a tool called EspC that uses local static analysis to catch locking violations in the program. And we have a tool called CSAL-Infer, which is an annotation inference and patching tool that can help jumpstart the effort on a legacy code base where you don't have any annotations. So what happens is, if you run CSAL-Infer, it automatically infers and patches your code with concurrency SAL, and then EspC becomes a lot more effective and accurate in catching locking violations in your program. So the question might be asked why we use SAL as a solution. So there are a few other approaches we explored. For example, manual review of code. We all know there can be a large number of paths in a given program. And in a multi-threaded environment, it's very difficult to figure out concurrency bugs just by manual inspection. Testing we found is ineffective for two reasons. One is there are oftentimes we find simple programming errors where a data needs to be protected by a lock. We acquire the lock, we write to the data, and we forget to release a lock in a certain path. These are the kinds of simple programming errors that we don't want to defer to till testing. Testing is also ineffective because sometimes concurrency bugs are very hard to detect and debug. They might result in non-deterministic failures. They might result in hangs only in stress tests. So mapping that back to the source code can be time-consuming and expensive. We also have global analysis tools like Global EspC, but it is heavyweight and time-consuming. It can take a week to provide results, which renders it a bit ineffective where we want to actually provide results right on the developer desktop at the compile time. So what we use is a local analysis tool called EspC, which can find all these bugs at the compile time. But to make it more effective, we use SAL, because SAL provides the calling context to the EspC toolset, which otherwise would limit its accuracy. SAL is nothing but a lightweight specification language that makes the implicit assumptions about a function explicit. So what happens is many a times we find people do provide locking side effects about a function in comments. Wouldn't it be nice to have a formal way where we can provide a formal language where we can specify the same comments, and at the same time the local analysis tools can take advantage of these? SAL does exactly that. We have a few annotations that we came up with. Like, I just wanted to show a few of them for concurrency annotations. We have acquires lock, releases lock, for example, provide function post conditions where functions to specify when functions acquire and release a lock as a post condition respectively. Similarly, we have function preconditions like requires lock held and requires lock not held, where in certain cases a function needs a certain lock to be held or not held before it is called as a precondition. And these two annotations let us specify these preconditions. There are also a group of invariant annotations. Sometimes the specific data needs to be protected by a certain lock, and we can specify this behavior using the guarded by annotation. There is also a lock level order annotation that can specify ordering on the locks. So whenever we acquire the lock in a reverse order, we can find out deadlock situations. There's also an annotation called low competing thread, because we have seen that in a multi-threaded environment, there are certain initialization functions or constructors that execute in a single threaded context. And no competing thread tells our tool not to worry about multi-threaded context when analyzing that function. So our tool is based on a very rich static analysis platform that's used for a wide variety of static checkers in Microsoft. So the beauty of this platform is that it abstracts out the high-level source language at the front end. So basically, it can parse C, C++, SAL. It can parse managed code using an MSIL driver. It can also parse JavaScript. And we construct an intermediate representation using control flow graphs. And when we have an analysis layer on top of the intermediate control flow graphs, which provides the tools for analysis. For example, we have an alias analysis engine, which can help us determine if two variable regions point to the same memory location. We have a pretty accurate symbolic path simulator called Symbolic Simulation Manager, which can accurately point out which are the feasible paths in a given program. And based on top of that, we have a group of checkers like EspC that checks for specific properties. EspC, for example, checks for concurrency properties. There are other checkers like null pointer. There are other specifications like checkers on top of that. So this is a very, very robust platform that's used extensively for writing static tools. So, the false negative rate is, so the criteria is that if we want to enable a tool on a developer desktop, or if you run it as a daily build, then the tool has to be 80% or more accurate. So what we do is, the warnings that we enable on the desktop have a false negative rate, false positive rate of 20% and less. And for false negative, it's not a, so for a developer desktop, it's not a big concern, because they don't cause a negative experience. What we want to make sure is we want to enable developers and make them realize that we are actually helping them find the right bugs. So we are more tuned and optimized towards reducing false positives, and not so much on, we haven't done any analysis on false negatives in that way. Yeah, but if we have the right annotations, then it is very, very accurate. The only scenarios where you will have false negatives is when you don't have a good annotation in your code base. Then sometimes in the calling context, you might not have all the locking behavior. And at that point, you might have false negatives. So the approach we take is we run EspC out of the box without any annotations. It provides value. Then you run CSAL infer to infer annotations, and you run it again in an iterative way. And it provides a lot more accurate warnings. So here we show how the lock sequence is computed in the control flow graphs. So at every point in the program, EspC keeps track of a set of locks that is acquired and released in the program. And then it does some checking for finding concurrency defects that I'll talk about in the next slide. I wanted to talk about a few optimizations that we had to make so that this can scale in large code bases like Windows, because otherwise we did have scaling issues. One issue is that we try to explore every path in a given function. And we found that that does not scale always. So one of the algorithms we use is to have a merging. So in a given path, if the property we are checking for doesn't change, then we merge the path into one. And this really helped in the scalability of this tool. There are also other heuristics we use. We try to determine if a given function actually is concurrent or not. And if it doesn't seem like an interesting function to analyze, we would skip that. The path simulation also is time consuming. So what we do is we first turn path simulation off, and then we try to analyze to find concurrency defects. And then we turn it back on to rule out the false paths, the infeasible paths. That way we can provide very accurate warnings at the same time in a very optimal way. We check for various classes of defects. For example, we check for cyclic locking to point out deadlock warnings. We check for insufficient locking to point out race conditions. We also find out if functions exit while holding a lock so that we can point out orphan lock warnings. I would like to talk briefly about the annotation inference engine that we have today. So we initially developed an annotation inference based on a SAT constraint solver. And when we tried to deploy it in Windows, it did not scale. So what we ended up developing is a hybrid tool which uses certain classes of heuristics to infer those annotations. in this particular example, you can see that the data, when we are writing to the data in process buffer, we are protecting it by the lock PCS. So EspC is smart to figure out that the data must be protected by the lock, and it infers the guarded by annotations on the structure. Next, about internal adoption in Windows. So today we run these tools on the engineered desktop. So every developer that writes code and compiles would have EspC running in the background process. And all these concurrency warnings would show up on the desktop. This way we are fixing thousands of warnings even before they are getting into the code base. We also run these tools daily as a build verification service. So even if a developer checks in a concurrency warning in the code base, we have a daily build verification service that would flag these errors, and the developer would need to fix these errors before code can move out of the branch. So this ensures we have a high quality product which doesn't have these concurrency warnings. It is used very extensively in Windows. In the beginning of Windows 8, for example, we added like thousands of concurrency annotations. It was a joint effort across all the feature teams that signed up for doing this work. We have also other divisions like Office, Windows Mobile, SQL, and the concierge team in DevDiv that have also used these tools. We are helping the ecosystem by shipping EspC as part of the VS11 code analysis feature. So this is available in the Pro and Ultimate versions of Visual Studio 2012. In this case, for example, we see a program where account is protected, the balance is protected by the lock CS critical section, and in the unsafe withdraw method, we are actually accessing that data without acquiring the lock. So EspC is quick to warn about the possible race condition. So this way, we do believe that by exposing this to external developers, we can help the ecosystem write better multi-threaded code. We have a bunch of resources externally. We have our MSDN documentation that talks about the concurrency SAL. This documentation is still work in progress that we are still finalizing, but you can still access it today and go through these annotations in details. We also have our team blog externally in Visual Studio Code Analysis. We also have a couple of talks that go into it's like a 1-hour talk, so it talks a lot more, it shows a lot more details about these tools in the Build conference last year. So you can also go and take a look at those talks. So what we covered today is a brief primer on concurrency SAL, and we learned that we shouldn't treat locking disciplines as afterthoughts. It should be very much part of an interface design. We learned that we should be using EspC toolset because for a Microsoft product, no corner case is rare. So we do want to avoid those hangs and non-deterministic failures at the customer's desktop. We also talked about how we internally adopt these tools in Microsoft because the cost of fixing a bug increases with time. It's cheapest to fix it at the developer's desktop. This way we can push quality upstream. We also talked about how we are shipping these with VS11 code analysis feature to help the ecosystem as a whole. So that's pretty much what I had.